After introducing what approximation algorithms are and seeing a first example on the vertex cover problem, we'll start seeing a few more interesting techniques to design such algorithms. And we'll do so mostly for now on the set cover problem, which is formally defined here. So it's we're given a universe. We'll assume here that there's n things in the universe. It's often convenient to take the first n integers, but that's will not be too strict about that. And then the input consists mainly of sets, subsets of this universe, so a collection of sets from elements in the universe. And in the general version, these sets have certain costs that we can specify. Then solutions are such that collections of subsets, or here formally the output is a collection of indices, so that if I take all the elements with indices in that set curly C, then I get as the union all of the universe back. So I have to cover the whole universe by making a selection from the sets I'm given. And the cost of such a selection is just the sum of all the sets costs, and that we want to minimize. Clearly, we would want for an input to make sense that at least if I take all of the k sets that they cover U, so otherwise the problem is not feasible, then certainly we want to minimize because I can always take all sets. And we assume the costs are weakly positive, say. There's a restricted version. You can either call it the cardinality version or the unweighted set cover version, where I guess the number, that's a weird version. The cost should be 1 for each set. We just count how many sets we take. I think I was jumping ahead of myself here. Unweighted set cover is a strict generalization of vertex cover, where we have the additional property. So as I mentioned yesterday, if you have some graph, let's maybe draw a short example. One way to think about the problem could be this. So a vertex cover has to cover all the edges. So the edges become this elements in the universe. And any specific vertex that I pick covers a certain subset of the edges, namely its neighborhood, or all the, I should say, the edges incident at that vertex. So if you have a vertex cover instance, it is a set cover instance, but it's a special set cover instance, namely every edge occurs in exactly the sets of its two endpoints. So it's not a completely general set cover instance, but one where every element of the universe occurs in exactly two sets. And we normally think of vertex cover as being unweighted, so we just count how many vertices we have to pick. But of course, you could define a weighted version of vertex cover. If you want to have a generalization that stays in the realm of graphs, you could say we were going to hypergraphs. In a hypergraph, edges become hyperedges, so just any subsets of vertices. And then clearly, you can always map an instance of set cover into a hypergraph where you have the vertices for the elements of the universe. 1, 2, 3, 4, 5, 6. And then you can draw, say we have a set that contains 1, 3, and 4. So that could be SI 1, 3, 4. And you just draw a hyperedge around those. And if you have a bunch of those hyperedges, maybe there's a few ordinary edges as well, and then you have a few of those, then you can ask what's the smallest number of them that I have to pick to cover all the vertices. This smallest. I guess these are the hyperedges. So am I confusing the picture now? Yeah. Each of these sets corresponds to some vertex that's contained in all of those. So I didn't draw the vertices. I should have drawn this differently. the hyperedges become the vertices. Is there a nice way to draw this directly from the sets? Okay, you know what? Let's leave it. I don't know if I can put it in a nicer picture next time. Either way, it's a generalization of vertex cover, and you can formally define it as a hypergraph, but it's not helpful by much. We're mostly using this is to illustrate things, but we'll also see that set cover can represent some other problems in terms of reduction. If you think about optimization problems and approximate solutions for them, a natural approach is to try some simple myopic greedy heuristic, which you should usually get some feasible solution from, but oftentimes you don't get a guarantee how good it is. And so it's a natural approach to say, let's start with a somewhat simple greedy algorithm and see if it is an approximation algorithm. And so we can do that for set cover as well. The natural notion of greedy here, for the fully general problem, if you want to take cost into account, I guess if you think about it for a moment, is that you want the best set in terms of cost per new element. You may have some collection of sets already, and then there's all the sets that you haven't picked yet, where you can choose which one to pick next. But some sets are more valuable than others because they give you a lot of new elements that you haven't covered yet and that you will eventually have to cover. And they do this at different costs. So it's not so useful to take an expensive set that only gives you a single new element if you could, for the same cost, cover several. I think that's the intuition. The intuition behind that is quite clear. You want the cost for each element that you cover to be small because you have to cover the same number n in total in any solution. So a formal way to greedily pick always the next best set in terms of the cost per new item ratio is spelled out here. We start with having nothing covered. C is the elements that we have already covered, and curly C is the indices of the sets that we used for that. So at the end, the curly C is the actual solution, but we need to keep track of how many elements we still have to cover. So as long as we haven't covered everything, we find a set that minimizes this ratio, the cost of the set divided by how many elements does this add to the covered elements. So the sets as I subtracted all the elements that we have already covered with other sets. And we find the one that minimizes this. That's the one we pick next. It's a greedy algorithm. We never take a step back. And we keep doing this until we've covered all elements. Here again, I'm assuming the instance is feasible, right? Otherwise, this while loop might never terminate. I think always in the following we'll make this assumption that if I take everything, then I get the universe back. There's a few annotations there that are kind of not part of the algorithm, but are useful for the analysis. The while loop is not a for loop with specific iterations, but of course you can speak about the ith iteration, just the way it's run. And we keep track of the price at which we covered certain elements. So alpha I is the cost per new item ratio of the set that we picked in the ith iteration. And for all the elements that we now gained in the covered elements C, for those elements we set the price at which we have covered them to alpha I. And so you can, immediate observation is that this price over time and the alpha i's can only increase because we're taking away elements that could have reduced the cost, and we're always picking the best current one. Now the key lemma to understand how well this algorithm works is this price lemma that tells us something about, say, the worst case of these prices for specific elements. And for that, we rename the elements in the universe so that they appear in the order that they're included here in the set C of covered elements. So this is what this order is referring to. And then it says the elements indeed become more costly over time. At least we have an upper bound for how much we have to pay to add this element to our set of covered elements. And it says in this algorithm, it's upper bounded by the cost of the optimal solution. But here this opt refers to the entire set cover. And it's divided by some term that when I gets bigger becomes smaller. So the overall upper bound here gets worse. Let's prove this. It's a simple proof, but I think it's insightful to do it briefly. Consider the time when we cover this jth element. Now, we usually cover those in batches of including an entire set, essentially in one time step gives you several elements, but we logically separate that into covering one element after the other. So before this element is included, we've had obviously j minus 1 elements covered because that is the jth one. So there were n minus j minus 1 elements left uncovered. We'll use this complement set going forward. Now, if you take any optimal set cover, curly C star, that one, even if I'm partway through my algorithm, I could always say, okay, I've made some initial decisions into my curly C, but for now, I'm just going to keep it as it is and add the optimal solution on top. Certainly, the optimal solution has to cover these remaining uncovered elements because it covers everything. And it does so at cost at most opt. It seems like a very crude argument, but we'll see it's essentially tight. So it means that there must be some set, and indeed it could be our set that we here pick in the minimization, which is, I guess, in the optimal solution, but not yet picked in our solution, where you can bound this this cost per new item ratio, and we can upper bound this by the cost of the optimal solution divided by the elements that are left to cover, because assume towards the contradiction this wasn't the case. There was no such set left with such a low cost per new item ratio. Well, then if you take this average cost per element and sum it over all the remaining elements, it means that you would need strictly more than opt divided by C bar cost if you sum it up over all those C bar elements, you would require strictly more than opt to cover just the remaining elements, but the optimal solution covers all of them at cost most opt. So that's a contradiction. So we always find a set Si star where the cost per new item ratio is at most opt divided bar C. And then I'm just inserting. So it's a relatively crude argument. We're just saying at any point in time, I could have continued with the full optimal solution, and that gives me a bound of how much I have to pay per element. If you plug this, if you put this together, you get an approximation ratio for the set cover problem. And what we get is an Hn approximation. So Hn is the harmonic number. And you will remember, maybe popped up in this module a few times, that this is, you can write it asymptotically as the natural log of n plus some infamous constant, and then a lower order term. That's the Euler-Mascheroni constant, 0.57 something. But the basic message is it's by and large natural log of n. So this is growing with n, right? It's not a constant factor approximation, and it's maybe not so great. But let's first prove it before we dismiss the result. So we want to bound the cost of our solution that the greedy algorithm finds. That's the cost is the sum of all the costs of the sets that we pick. And I can rewrite that as the price at which I included all the elements. That's just here I'm summing over the cost of the sets. here I'm summing over the elements. Now, some elements are covered by multiple sets, but the price is defined such that it only takes the new elements into account. So when I cover some elements several times, right, so here's my universe. Say I'm first covering these elements. The three of them share the cost of this set. If the next set is taking these elements, only those two new elements share the cost of this new set. So it's just rewriting the sum over the cost of all the sets that I pick. And now, of course, we use our price lemma to upper bound the price. That's a simple calculation then. And you pull out up, which is a constant factor, you're left with that sum, and that's exactly the nth harmonic number. So it's a very simple analysis. No fancy math needed here. But I really want to stress again, this was just the simplest greedy algorithm that if for the weighted version of set cover, it's the most natural thing to try. Always pick the element that gives you on an amortized cost per element that you gain the best next step. But really, an approximation guarantee that grows with n is not so great. Could be a large factor if the input is big. Unfortunately, this is essentially the best we can hope for again. In the worst case, you can consider, for example, the following instance. It's a star graph. The worst case instance is indeed a vertex cover instance where every element in the universe occurs in at most two sets. But I need here a weighted version of vertex cover, and the weights are chosen so that this fails. So I'm putting a weight of 1 plus epsilon here on this center of the star. And then I'm putting harmonically increasing weights on the elements around the star until I have 1. And so what happens in the greedy algorithm is initially this vertex looks, this singleton set that just gives me this one edge. It looks really attractive because it's very cheap. Whereas this other guy here would give me n edges, but at the price of 1 plus epsilon. So the cost per element for the center initially is 1 plus epsilon divided by n, whereas the leaf has 1 over n, so that wins. So I'm going to pick that leaf in the greedy algorithm, and then the same thing happens again. I have one less element to cover, so I have 1 plus epsilon divided n minus 1 in the next step. And so again, this leaf appears cheaper to the greedy algorithm. And so it picks all the leaves around there, all the n sets, whereas I could have picked the center at the start. So the optimal cost is 1 plus epsilon, which is obvious here. But the greedy set cover decides to pick all the leaves around there. You can even boost this construction for the unweighted vertex cover problem. That's more tricky, and I don't think that's super insightful, but it's a nice puzzle to think about. You can show even if you take the unweighted vertex cover, then the greedy algorithm, as we've shown it, is not going to work well. Of course, you can do better on vertex cover. We've seen the approach with matchings last time. But if you so this is for greedy. You can show that this specific algorithm is not doing so well. This kind of logarithmic growth seems inherent.